Okay. I welcome you all to yet another week of Principles of Downstream Techniques in Bioprocess. This is our fourth live session in a series of 12 classes. So, we'll be looking into the practice assignment for this week, covering the topic solid liquid separation problems, pre-treatment and filters, and absorption. Let's start with the first question. To reduce filtration rate, what should you do? A. Increase the bed porosity, decrease compressibility, decrease cake resistance, or D. Decrease filter cloth area. Think about it. I'll give you a minute to uh, give the answer. And please resort to the chat box to type in your answers because there's no point in me just speaking and you just listening, right? We both need to know what your thoughts are, what others' thoughts are, so that we can correct or debate on what's the right answer. I'm still waiting for answers. All right then. So to reduce filtration rate or to slow down the process, what would you do? What are the steps that you can do to reduce the speed or the filtration rate? So you're essentially slowing down the process, right? So if you increase the bed porosity, what will happen? If the sieve size is smaller, then the filtration rate will be low. But if the sieve is bigger, then filtration is fast, right? Whether it actually filters what you the way you want to filter is another aspect, but the rate of filtrate falling through this filter mesh as such, or the filter material or filter medium is going to be fast. So if you increase the porosity, or in other words, if you increase the sieve size, what is going to happen? Filtration is going to be faster, right? So that is wrong. Correct. Option B, decrease the compressibility. So what is compressibility? Above your filter medium, this color is visible, right? You want me to use something else? So let's say this is the filter medium with all the sieve pores, and your fermentation broth with all its multiple solids, different materials is going to fall on this, and this is going to form a cake over time. Correct? And you're going to have clear filtrate coming out. So, the greater the compressibility, greater is the resistance, right? If something, let's say, if you have solids that are not so compressible, which means they are hard enough so that any amount of pressure is going to still leave a little space between them for the liquid to percolate through. But suppose if the cake material is very small, that over time with pressure it is going to get compressed even more. So with higher compressibility, the cake is going to be very thick. It is not going to leave much space for the next batch of media to filter through and come out. Correct? So if compressibility is more, filtration is going to be less. But if compressibility, let's say compressibility is inversely proportional to rate. So which means if you decrease compressibility, rate is going to increase. And what do you want to do here? Decrease, right? You want to reduce the rate of filtration. So again, this is a wrong answer. Option 3, decrease cake resistance. So what happens now? Instead of compressibility, you are decreasing cake resistance, which means it is going to be even more compressible. Correct? The cake is, so you're going to have this case. When the compressibility is high, the cake is going to compress under pressure over time and it is going to form a thick layer. So you can argue that this will slow down filtration, right? Yes or no? Okay, let's put that on hold. Decrease filter cloth area. Obviously, filtration is proportional to time is equal to V square into viscosity. So what happens when the cake resistance comes down? I mean, what happens if you decrease the filter cloth area? Since it's the denominator, if you reduce the area, again the time is going to increase, right? So does that slow down? True. Does decreasing cake resistance improve filtration rate? So you add filter rates to increase the resistance, right? If you are resisting the flow through, on one side it is going to keep filtration easier, but on the other side the cake thickness will also increase with increase in resistance, right? If the cake resistance increases, the cake thickness will also, uh, how do you say that, cake deposition rather than thickness also increases. Although this is true to an extent, it is not a real solution for filtration rate, because when the cake resistance decreases, it is more of a compressible, the compressibility increases, right? When resistance decreases, compressibility increases, and compressible cakes are tough, or they deposit over time and the filtration rate will reduce, but you cannot, it depends from case to case, and whether any filter aids are added and other parameters also, right? So the sure shot answer, if it's a multiple choice question with just this option, I mean with just one option, right, you should go for decreasing filter cloth area, which is the most obvious. Decreasing cake resistance can sometimes aid to reducing filtration rate. Okay. Again, decreasing cake resistance, if it has filter aids, you can still continue to improve the flow rate, but the cake deposition is going to continuously increase with use of when the media keeps adding with continual use of the filter. Shall I proceed? Let's look into question 2. Filter rate decreases the bed compressibility factor from zero point 0.5 to zero point 0.3. What will be the filtration time if the pressure applied is 16 bar and original time is 16 hours? Do you want to take a minute to answer? Let me put in the formula for you meanwhile. So filtration time again is T is equal to V square. T is equal to V square mu SC rho naught whole divided by 2A square delta P. So I'm going to separate the variables here because the knowns are compressibility factor is given, SC is given, delta P is given, and the original time in hours is given. Right, so I'm going to separate the variables in such a way that T is equal to V square mu rho naught whole divided by 2A square. Let us have this as a constant into SC by delta P. So for the first case, we know that time is 6 hours and pressure is 16 bar, and what else do you have? Compressibility. SC1 is 0.5. Correct? Has anybody found the answer? So let's call this constant. Right, so I'm going to substitute the values for this. So 6 is equal to this constant into what is SC? 0.5 divided by delta P is 16 bar. So I'm not putting the units here. 6 is in hours, 0.5 is compressibility, and 16 is in bar. So which means the constant, which is V square mu into rho naught whole divided by 2A square is equal to 16 bar into 6 hours whole divided by 0.5. What is that? 16 into 6 is 6 are 36, 3 1 6 6 is 3 is 96 divided by zero point 0.5, that's 180 plus 12, 192. Is that right? Bar hours. The units don't matter here because I'm going to use the same equation to substitute the same things, but you can carry it forward. Now going to the second part, what are they asking? When the filter rate decreases the bed compressibility factor from zero point 0.5 to zero point 0.3, what will be the filtration time? So T2 is what you need. Again, T2 is equal to same constant into SC2 divided by delta P2, and there is no mention of the pressure changing, right? The only factor that changes is the compressibility factor SC. All other parameters are the same. So we'll be using the same constant which is independent of any of because the area is not changing, the volumetric flow rate is not changing, and or the volume of media that is getting processed is not changing, the viscosity or the density is not a question here, correct? So instead of calling it P1 and P2, I'm going to just call it delta P, right? So what do you know the constant as? V square nu rho naught by 2 a square into SC2 by delta P is equal to 192 bar hour into, what is SC2 here? Zero point 0.3 divided by delta P is 16 bar. Let me write the given here as SC2 is equal to zero point 0.3. Anybody worked it out? Is equal to, I'm going to cancel the bar here, so you'll get your final answer in hours. I'm going to use my calculator. 192 into zero point 0.3 is 576. 576 by 16 divided by 16 is 3.6 hours. Am I right? Is this the answer that you all get? Should we check? The range is between 3.2 to 3.6. So we got the answer as 3.6 hours. Shall I proceed to the next question? Guys, you should really respond. This is a live session for a reason, right? I'm right here. You can ask me something. You can say this is wrong, this is right, I disagree. Correct? Okay, I'm going to proceed to question 3. In cross flow filtration, what is not correct? Liquid flows parallel to filter cloth, no cake bed is formed, solids escape through the cloth, and pressure drop is low. Think about it. I'm just going to draw a schematic here. Again, I'm waiting for your answers. Please don't wait for me to get to the answer. Feel free to type in your answers in the chat box, and it's not going to get graded or anything. Still waiting. You're going to have all sorts of. Okay, let me continue to explain. So, in a parallel cross flow filtration, the liquid flow is tangential to the filter medium, right? So it's going, the flow is going to be parallel, correct? And then the retentate is going to stay here, and filtrate will come through the other side of the cloth, correct? So let's look into the options. Liquid flows parallel to the filter cloth, is that correct? It in regular filtrations, gravitational filtration, you have liquid flowing through and filtrate coming out, right? You have all the impurities here, it might form a cake. So the fluid flow is perpendicular to the filter medium. But in case of cross flow filtration, the liquid flow is parallel to the filter medium, isn't it? So that is true. Next, no cake bed is formed. Compared to what you get here in perpendicular filtration, you are not going to get as much cake formation here, because the liquid is by itself, it's coming under some pressure, right? So it's going to push whatever deposit that might form on the filter medium. Therefore, cake bed is very, very minimal, or you can even call it no cake bed is formed. Again, this is true. Solids escape through the cloth. So the whole point of filtration is to keep the solids from coming through, and you are going to allow only the liquid to flow through whatever the medium is, whether it is cloth or other sieve, whether it is polymer mesh membrane, whatever it is. So this is not true, correct? And pressure drop is slow. Yes, compared to what resistance you face in a perpendicular flow, either given by the filter medium or by the cake or by any filter aids, is going to be very minimal in case of parallel flow, right? So the delta p between this is going to be much lower than compared to the delta p here, correct? So the pressure drop is low, which is again true. So the only option which is not correct is option C. Can you all agree with this? Solids escaping through the cloth is the wrong answer for cross flow filtration. I mean, this is the wrong statement and the right answer. Correct? Okay, let's move on to question 4. Adsorption is independent of pressure when A. All the sites are occupied, B. At low pressure, C. When the adsorbent is a fine powder, and D. Temperature is very high. So often you find that. So beyond a certain pressure, adsorption becomes independent or constant. So what can the reasons be? All the sites are occupied or at low pressure. I mean, obviously this is wrong, because at low pressure it is dependent on, I mean, adsorption is affected by pressure, right? You cannot say that adsorption is independent. So right there you are going to cross off option B. So when the adsorbent is a fine powder, so does that matter? We look into it. Temperature is very high. So as far as adsorption, both physical and chemical, are concerned, in physical absorption, with increase in temperature it decreases, right? Because it's yeah. So why does it decrease? Because it is an exothermic process, correct? Adsorption is an exothermic process, so with increase in temperature it is unfavorable, therefore adsorption decreases. In chemical adsorption, With temperature, first there's an increase and then it decreases. Slight increase and then it decreases. So this is chemical. Is my font size too low, too small? Let me bring out the axis here and write chemical adsorption. Right? So at temperatures very high, you're not going to have independent an absorption rate that is independent, or an absorption which is independent of pressure. Correct? So again, it is wrong. So whether is it A or C? When the adsorbent is a fine powder, does it exclude it from being under the effect of pressure? Not necessarily, right? But why does the curve even attain a stable or a plateau when the pressure is high? So what are we talking about? Let's say a material has multiple sites to absorb a certain molecule. It only has so many sites, right? So let's say it can absorb to one, two, three, four, five, six molecules. So with increase in pressure, first maybe two molecules might adsorb. Then with a further increase in pressure, some more are getting adsorbed. With even more increase in pressure, two more are getting adsorbed. But there are so many adsorbate left in the media, and you are still increasing the pressure, but you see that none of them are adsorbing onto the adsorbent, right? So what is the reason? Because you don't have any more. This is my adsorbent, and the blue ones are my adsorbate. Correct? If you don't have any more sites to accommodate adsorption, then no matter how much pressure you increase, the adsorption cannot improve. Correct? So that is the reason for this plateau formation. So all sites are occupied. Clear? Shall I proceed? Question 5. If the relationship between 1 by fraction of surface covered and 1 by pressure is not linear, then the adsorption is. Take a minute. If the relationship between 1 by fraction of surface covered and 1 by pressure is not linear, then the adsorption is linear. B. Freundlich, C. Langmuir, and D. Zero order. So zero order is when it's a constant and independent of anything. What might the answer be? And immediately they've told you that it's not linear, then the adsorption is. So obviously it's not going to be linear. Is it Freundlich, Langmuir, or zero order? So to help you, x by m is k into e power 1 by n. This was the equation for Freundlich isotherm, right? So it's non-linear means this 1 by n is not equal to 1, or n is not equal to 1. It has some other value. Now they're telling you fraction of surface covered. So the adsorbate by adsorbent. So 1 by fraction of surface covered will be m by x, correct? And 1 by pressure will be 1 by p. And this has some n or m factor which is not equal to 1. Alright? So what does this follow? It's the Freundlich isotherm, right? Langmuir on the other hand is Kp by 1 plus Kp. Yes or no? So Langmuir is wrong, zero order is wrong. It's the Freundlich isotherm. Okay, question 6. For a reaction to not be spontaneous, remember to read the not. Delta G will be 0, negative, positive, none of the above. Think about it. This is one of the easiest questions in the assignment today. I expect some answers in the chat box at least for this one. Guys, so the delta G or free energy is spontaneous when gives free energy, right? When do you call a reaction spontaneous? When the delta G is negative, correct? So 0 is wrong, negative is not to be spontaneous. So if it is negative, the reaction will be spontaneous. If it is positive, it cannot be spontaneous, right? None of the above, obviously, we are going to omit, skip, or reject. So the answer is option C. Agree? Okay, question 7. Which of the following statements regarding the physical adsorption of a gas on surface of solid is not correct? A. On increasing temperature, adsorption increases continuously. B. Enthalpy changes are negative. C. Adsorption is specific. D. It is reversible in nature. Which are the following statements regarding the physical adsorption of a gas on surface of a solid? I have already answered this question while explaining a previous question. So think about it. Take a minute. You can even unmute an answer if you are shy to type it. Thank you, Anjali. Is Anjali right? Does anybody want to give some other answer? Is adsorption specific? Yes or no? Yes, right. Otherwise, you will not be using specific adsorbents for specific uh, adsorbates. Right? It is specific to a certain extent, especially if you're talking about chemical adsorption. It is very specific. Even in physical adsorption, you need to have, uh, although it may not be extremely specific, but it has to react enough, or the van der Waal forces of attraction should be there for it to adsorb on a particular solid. Correct? And for chemical adsorption, obviously, you will need a certain degree of specificity for it to adsorb. So, is it specific? Yes. Is it reversible in nature? Yes, again, right? Otherwise, you wouldn't be doing adsorption. If it was, I mean, you will not use this as a downstream step if you cannot recover whatever you're trying to absorb, even if it is toxic. See, if it is, if you're absorbing something that you want, then you will want to recover it back from the adsorbent again later. If you're going to absorb something that you don't want, obviously you don't want to take that particular toxins from the adsorbent, but you really want the adsorbent back. You cannot keep buying new adsorbents, right? So again, yes, it has to be recoverable. I mean, it has to be reversible. Only then you can either reuse the adsorbent or recover whatever you are looking for. Correct? So it has to be reversible. So adsorption is reversible, adsorption is specific. And enthalpy changes are negative. Yes, we did see that delta G is delta H minus T delta S. And entropy decreases because it is moving from a happy free place to the solid that adsorbs, right? If you call this the adsorb, let me write that again, adsorbent. So those molecules are actually losing their freedom and they are going to restrict themselves to the adsorbent surface. So the entropy decreases, it's negative. So therefore, this whole term turns positive, correct? It becomes delta H plus T delta S, which means enthalpy has to decrease, it has to be negative, and the net, how do you say, the modulus of enthalpy should be greater than the physical value, just the value of T delta S. Therefore, enthalpy changes are negative is true. So which of the following statements are right? On increasing temperature, adsorption is not going to increase continuously. Even for chemical, it is going to decrease after a point. In physical, it decreases right from the start. Correct? Therefore, your answer is, I mean, I should cross all these because these are true. And the only thing that is not correct is A. Correct? On increasing temperature, adsorption increases continuously. So Anjali is right. Question 8. I require 1.2 grams of adsorbent to adsorb 80% of an impurity from a solution. How much adsorbent would I require to adsorb 90% of the same impurity? All other conditions are same. Assume linear adsorption isotherm. So, sorry, oops. I think that got same. So I'm going to continue here. Cool. So you're having a linear adsorption isotherm. Let's say we have here adsorbent and adsorbate. So you have the value that you require 1.2 grams to take out 80% of adsorbate. Now, since it's linear, The slope is going to be common for both, right? I can use the proportionality to arrive at the answer. Does anybody want to try this? So the question is, how much adsorbent would I require to absorb 99% of the adsorbate impurity here? Okay, what is this? It's the question. So you can use this particular slope as a measure to get this. So you can use the general rule since it's linear. So for 80%, I need 1.2 grams. What do I need to get 99%? So x is equal to 99 into 1.2 divided by 80, and we're going to get it in grams. Can somebody work this out and tell me the answer? Use your calculator if you must. What's the answer, guys? 99 into 1.2 divided by 80 gives. Thank you, Sriram. Thank you, Natarajan. 1.485 grams. Right? Shall we check the answer? It's between 1.3 and 1.6 is the range given. We got 1.485 grams. Great, guys. Let's move to the next question. For adsorption to be spontaneous, delta H should, we just answered that question in the previous one, right? Should it A increase, B remain same, C depends on adsorbent type, or D decrease? So delta G is delta H minus T delta S. So for it to be spontaneous, this guy is going to be negative. So think about it. How should H be? Should it increase, remain the same, or depends on adsorbent type or decrease? A or B or C or D? Just type in the option that will do. We just discussed this, no? So when the adsorption process happens, as it continues, delta S is going to decrease. It is going to become negative. So which means this entire term is positive. Therefore, it falls on delta H to be more negative and drive the process forward. In order to make this spontaneous, delta H has to be more and more negative, which means it is going to decrease. Correct? So it does not increase, does not remain the same, because after a point it will become non-spontaneous and it cannot increase. And it is not, the value might depend on the adsorbent type, but the trend should be to decrease, right? Question 10. In landmark adsorption, at high pressure values, the relationship between pressure and surface coverage will be. Is it A independent, B non-linear, C linear, or D quadratic? So, for those of you who are forgotten, this is the Langmuir absorption isotopes relation. So, at high pressure, so Langmuir's absorption always is applicable only at low pressure. People say that at a high pressure the relation is no longer that correct or accurate or valid, right? So if you remember from the lecture, when pressure is very low, so very good Chelsea. So when the pressure is low, you can say that theta is almost equal to kp, because it's very small that you can take it to 0 and the denominator is 1. But when the pressure is high, this term becomes negligible, right? Because this value is quite big. So addition of 1 is not going to make much difference to this big denominator. So theta is equal to kp by kp, just 1 is a constant, right? So it's of zero order reaction. It is not going to be dependent on pressure anymore. So whatever the pressure may be, it is just independent. Obviously, Langmuir adsorption isotope at any pressure is not going to be non-linear or linear. I mean, linear to an extent you can say, because yeah, you cannot say because there is no proper m here. It's just a constant. It's not dependent on. There is no pressure term at all. And it's not quadratic, obviously. Therefore, it is independent. It has no relation. At high pressure, the relationship between pressure and surface area is independent. Correct? With that, we come to the end of week 4's practice assignment. If you remember, I had not solved one of the questions in week 3. This one, I have posted this answer in the PDF that I uploaded for week 4, but I don't know how many of you checked. So I'm going to go ahead and answer this question again. So last time the mistake that I did was I used this particular relation, C is equal to C naught into 1 minus e power minus kdv. Correct? So this might be used when we are talking about a cell getting killed and releasing the contents. And we are not going to use KD there, it will be KT. But since we are talking about enzyme deactivation, I shouldn't be using this. Rather, I should use the relation C is equal to C naught e power minus KDT, where KD is equal to A e power minus ED by RT, where D is for deactivation, correct? And again for CA, it will be CA naught e power minus KDT, and CB it's going to be CB naught into e power KT is equal to 0, where Shriram, it's not 0. Did I write KT is 0 somewhere? Can you type in your question, Shriram? Minus KDT. Now you know that KD for A. In case of A, they're saying KD is equal to K. In case of B, KD is equal to 2K. See, I'm assuming you all know what the question is. Do you want me to repeat the question? Those who did not join last week. Two lipases A and B initially at equal concentrations. So they're saying that C naught is the same in both cases. C naught is equal. And the deactivate with deactivation rate constants of K and 2K respectively. So what does that mean? KDA is K and KDB is 2K. What will the relationship between the concentration CA divided by CB? So CA by CB what relation does it have with T? As a function of temperature, what relationship does it have? That's the question here. So this is the relation that we are going to use. So I'm going to substitute these two there. Ca is equal to Ca naught e power minus Kt, and Cv is equal to Cv naught e power minus 2Kt. I'm going to divide these guys. So Ca by Cv is equal to Ca naught by Cv naught into e power minus Kt divided by e power minus 2Kt. So I'm going to cancel Ca naught and Cv naught because C naught is equal in both cases, right? So we are left with e power minus Kt, and if I take this to the numerator, I'm going to have plus 2Kt, correct? So I can take it as e power 2k minus k into t, right? So that's going to be e power k into t. Is one more Ca by Cv. So as a function of t, how is it related? Son, Ca by Cv is related to the exponential function of t, right? This is constant, obviously, so it is related by e power t or exponent t. So B is the right answer. All the others are wrong. So we had this particular equation in your. I have snipped this from the lecture notes and put it here for easy access. I taken the C naught to the numerator so that we can divide comfortably. So is that agreeable to everybody? So that I end my today's class. If you have anything else to ask me or tell, you can go ahead. Please don't feel shy, and thank you all for joining this session. I'll be looking forward to meet you all in the next forthcoming sessions too. All right then. I'm going to close down. Thank you very much. Okay. Good night. Have a good weekend.